For years, Saturn's largest moon, Titan, has been the poster child for a truly alien ocean world. We saw this hazy orange marble in space and thought, wow, there's a colossal secret hidden under that ice. And for a long time, we thought we had it all figured out. But it turns out, the truth about what's inside Titan is way stranger and, frankly, a lot cooler than we ever imagined. So let's break down what we thought we knew and the incredible news story the data is telling us now.
So when the Cassini spacecraft sent back these amazing detailed maps of Titan, we saw this incredible landscape of methane rivers and dunes of frozen hydrocarbons. But as cool as that is, the real mystery wasn't on the surface, it was deep inside. The biggest question of all was, what is really going on under that crust?
And for a very long time, the answer seemed obvious, it was compelling, and it was super exciting. The leading theory, the one you'll find in most textbooks, was that Titan was hiding this gigantic, planet-wide ocean of liquid water, neatly sandwiched between thick layers of ice. Okay, so the first big piece of evidence came from this physics concept called the moment of inertia. The best way to think about it is to picture a figure skater. You know how when they're spinning, they pull their arms in tight? That concentrates their mass at their center, and they spin way, way faster. Well, by watching how Titan wobbles as it orbits Saturn, we can do the same thing. We can figure out how its mass is spread out inside. And this was the magic number that came back from Cassini's gravity measurements, 0.342. Now, a number's just a number, right? But this told a story. See, if Titan were just a solid, boring ball of rock and ice mixed together, its MOI would be higher, somewhere around 0.39. This lower number was a huge clue. It meant that the heavy stuff wasn't evenly spread out. The denser materials had to be packed in toward the center.
What that number told scientists was that Titan's interior was partially differentiated. Basically, all the dense rocky material had tried to sink to the middle, but something stopped it from forming a perfect solid core. It strongly suggested that there was some kind of layer in there that was, decoupling the outer shell from the deep interior, letting them move a little bit independently of each other.
And all of that evidence led to this really elegant, widely accepted model that we called the ocean world. It went something like this. At the very center, you've got a dense core of rock that's soaked with water. On top of that, a layer of weird high-pressure ice. And then, the star of the show, a global ocean of salty liquid water. And floating on top of all of that was the outer crust of regular water ice that we see. And look, this wasn't some fringe idea. This was mainstream science. Back in 2012, NASA's own Jet Propulsion Laboratory put out a statement saying the data made the strongest case yet for this ocean. The evidence looks solid. For all intents and purposes, the case was closed.
But then, a new clue started to emerge, and it came from digging back into that very same Cassini data, but looking at it in a new way. There was this tiny detail, an anomaly, hidden in the way Titan flexes and groans under the massive gravitational pull of Saturn.
So think about it. Every 16 days, Titan makes a trip around Saturn, and the whole time, its gigantic parent planet is constantly pulling and squeezing it, like a cosmic stress ball. This gravitational tug-of-war creates what we call tides, and it turns out the way Titan responds to this constant squeezing was the key to completely unraveling the ocean theory.
This brings us to a concept called tidal dissipation. It sounds complicated, but it's not. Just take a paperclip and bend it back and forth, back and forth. What happens? It gets hot, right? That's friction turning motion into heat. The exact same thing happens inside Titan. As Saturn's gravity flexes it, internal friction creates a ton of heat. We measure this friction with a Q factor. All you got to remember is this. A low Q means high friction.
And this is where the beautiful ocean theory just slams into a brick wall. Every single computer model that included a global liquid ocean predicted that Titan should have very little internal friction. I mean, an ocean would basically act as a lubricant, right? Letting all the layers slide past each other easily. But when scientists actually measured the friction inside Titan, they found it was shockingly high. The reality just did not match the theory. At all.
This wasn't a small problem. This was a showstopper. That really high level of friction was a direct contradiction to the ocean model. A global ocean would dramatically reduce the amount of friction happening deep inside the moon. So you have the data screaming that there's a lot of friction, and you have the theory saying there should be almost none. Both of them just can't be right.
And then the new analysis delivered the smoking gun. I mean, look at this. Scientists modeled what the data should look like with an ocean and what it should look like without one. Now, see that black oval? That's the real measurement from Cassini, and it lands smack dab in the middle of the no ocean camp. It completely misses the ocean model. It's not even close.
And the authors of this new study, they didn't mince words. They put it very bluntly. These new measurements preclude the existence of a subsurface ocean on Titan. The evidence was so strong, it didn't just question the old idea. It completely overturned it. The ocean was gone.
Okay, so if there's no ocean, what in the world is actually down there? And this is where it gets really, really cool, because the new data points to a solution that actually explains everything: the weird moment of inertia and the high friction, all in one neat, unified model.
So, say hello to the new Titan. At its heart, you still have that big, low-density core of waterlogged rock. On the outside, you have a thick, solid shell of normal water ice. But the secret ingredient, the layer in the middle, it's not a liquid ocean, it's a thick layer of high-pressure ice that is warm, squishy, and basically slushy.
This slushy ice layer is the key to the whole puzzle. It's so close to its melting point that it's not totally solid anymore. It's soft and deformable, kind of like very, very thick cosmic taffy. So as Saturn's gravity constantly kneads and squeezes this layer, it generates a massive amount of friction. This is the source of all that heat, that high tidal dissipation that Cassini detected.
And how much heat are we talking about here? About 4 terawatts. That number is just staggering. To give you some perspective, that's more than 10 times all the heat being generated by the natural radioactive decay of elements in Titan's rocky core combined. This internal friction isn't just a side effect, it's the main engine heating the moon's interior.
Ultimately, this huge discovery forces us to completely rethink our definition of an ocean world. It has these profound implications, not just for how we see Titan, but for the entire search for life beyond Earth.
You know, let's just compare Titan to Ganymede, which is Jupiter's biggest moon. They are almost identical in size. They're practically twins, and yet their insides are probably completely different. Ganymede most likely does have a global ocean, maybe because it had a much more violent past with more tidal heating. It just goes to show you, being a big icy moon does not automatically mean there's an ocean inside. Every single one of these worlds has its own unique story.
But does no global ocean mean no chance for life? Absolutely not. In fact, this slushy, high-pressure ice layer could be an even more fascinating place. It could host countless little pockets of liquid water, creating these unique habitats, these cryoecological niches. You could have vigorous convection in this warm ice, dredging up nutrients from the rocky core below, creating a dynamic environment that, in a weird way, kind of resembles the vibrant ecosystems we find in Earth's own polar sea ice.
This whole story is just a perfect, beautiful example of the scientific process in action. We build a model based on the evidence we have, we go out and get better data to test it, and sometimes we have to be willing to throw out the old, comfortable ideas and embrace a new, more accurate reality. It leaves us with a really humbling and incredibly exciting question. If we were this wrong about Titan, the icy moon we thought we knew best, what other fundamental things have we assumed about our solar system and the universe that are just waiting for the right data to be completely rewritten?